Hello, and thanks for watching. Today we're going to talk a little bit about simple machines. And so this is a video presentation put together for the COVID-19 stay-at-home activities, but this can be used just to introduce you to a few things. And so this is going to be part one of two. So we're getting into a little bit more advanced topics. We're bringing some science and math into the shop, getting some things done with work and mechanics. So part one of a two-part series. Moving forward, our goals today, and with this video, you should be able to understand mechanical advantage. And with this, I'm going to skip through a lot of my PowerPoint slides to skip over the fractions and the math. So as you can see in these goals, the fractions and the math and the understanding of the equilibrium and how to equate this in an algebraic formula is not today's goal. So please don't get overwhelmed by that. If you are comfortable with that and you've been in a physics class and you want to dig a little deeper as far as how to keep things in static equilibrium, you can check out the other slides. And I also have I have a worksheet that goes along with this that could challenge you to figure out lever lengths and weights and masses and things like that. So get at me if you want that. The next goal is going to be just looking at inclined planes, understanding that. That's what we're going to use as our example to kind of understand mechanical advantage a little further. And then we're going to look at a screw system. And the reason we're going to talk about the screw system and skip the wedge is because we talked about a car jack last week, and one of the car jacks we had was a screw jack. And so I want to talk a little bit about that. And then I think it's important for every person to understand how to identify a screw. So when you go to the hardware store and you're trying to fix something at home, you are capable of communicating what your bolt or screw looks like, or you can take it in and understand how things are organized. So moving forward, let's talk about mechanical advantage. Here's some quick pictures of three of the six simple machines. So we're talking about mechanical advantage. Why have these things been designed? Because humans or other animals, horses, aren't strong enough. And so we have to develop some sort of method to give us an advantage. And a lot of the times that's a mechanical system like a plane, a ramp. We see this a lot around semi-trucks, a wedge. Next week, we're going to talk about splitting firewood, what seasoned firewood means, and then also how you can do that with a hydraulic splitter. So we'll talk about hydraulics. And then, like I said, there's the scissor jack or the screw jack for that you see a lot in cars that maybe you saw last week if you participated in the learning. So moving forward, one of our goals is mechanical advantage. So all mechanical advantages that we need to think about is how we are obtaining an advantage over what's happening in front of us, and we're going to represent that as a ratio. And so as long as we're comparing apples to apples, oranges to oranges, we're not going apples to oranges. As long as we're focusing on specific things, we can compare them in a ratio. So right here, the ratio of the magnitudes. So here's the magnitudes is what it's talking about. And then we have resistance and effort. So we're going to see we don't see M as the variable, we see F. And then we're going to see R and E as sub variables. I think I used the correct term there. Anyways, and so I'll show you that as far as what it looks like in the math, just so you understand what you're looking at in the math. But again, that's not our goal. Next, mechanical advantage, ratio of the distance traveled by the effort and resistance force. So now we have D for distance. And so that'll be our variable capital D with lowercase e, or excuse me, they're still uppercase, but they're a subscript, E and R for the resistance and the effort. So again, apples to apples, oranges to oranges. We just got to make sure we understand where we're putting stuff in our algebraic formula if that was our focus. And then next thing, this is what is allowed. If we understand these things, then we're able to, as engineers, mechanical technicians, aviation technicians, we're able to design things further so that way we can, think about speed, distance, force. All right, so the first example is going to help us a little bit more with mechanical advantage. This is an inclined plane. Picture you on the left box that's a little bit more orange because it's in the shadow at the beginning. Picture you lifting that left box straight up. Our goal is to get this box to a certain height. Both boxes get to the same height. However, one box just goes straight up against gravity. So that's kind of the blue line, is that force line, equal and opposite resistance. The blue lines are equal because gravity is pushing down at the same. The red lines are the effort force. So those effort forces are different because if I just have to go straight up, I have more effort just going up in a vertical motion. If I'm pushing up a ramp with an assistant, let's say, excuse me, let me rephrase that. If I'm pushing up the ramp and using the ramp as an assistant, not somebody else, then I'm putting in less effort, but I'm going a further distance. So I made a compromise as a human, and we're going to see that a little bit in the algebra. I made a compromise to push the box a further distance, but I exerted less force, and so it probably was easier on my body. And so this is where ergonomics would come in if you were going to talk about inclined planes and safety in the workplace. So that's what those arrows are. Those are our force arrows. And so back up to the top in black font, it says we have an MA, mechanical advantage. I'm going to start now referring to as MA. It has an MA of 4-to-1. And so what is that telling us? So that's telling us that the force, like I mentioned, the effort force is 4 times less than the magnitude of the resistance force. So we're focused on the more yellow box, the one on the inclined plane. And you can see that the arrow looks about a quarter of the size or 4 times less than the blue one. Now, if we think about the distance, again, to repeat kind of what I said before I put up these bullet points, distance traveled by the forces, if we compare these, just the distances, the effort force 4 times greater than the distance, effort force travels 4 times greater than the resistance force. So again, that's what I was talking about, compromising distance for effort. So we just increased the distance 4 times longer, but that's okay because our body didn't have to work as hard. So hopefully that helps clarify a little bit about mechanical advantage. If it doesn't, please press pause in the video, go find a Google resource, Wikipedia, find another video, and if you think it's better than my video or this little PowerPoint, please share it with me, and I'll do that in the future. So go ahead and click pause. We're at 7 minutes, and then I'm going to go ahead and move forward into some of the other pieces of this. Okay, so the thing I want to finish with mechanical advantage now is, since it's a ratio, our magic number is 1. You could think about that as like 100%, but 1 is our magic number, and all that has to do is with proportions as far as what our give and take is. Similar to our boxes we just did back here as far as 4-to-1, and then we're increasing the distance 4 times. And then if we increase the distance 4 times, then proportionately, we're going to have 4 times less effort going into that box if we made the distance 4 times greater. So that's all this is saying in a lot of fancy terminology. So hopefully this doesn't confuse you too much. But it's basically, if we were going to have a goal today of being math-based with these formulas, we would get a final result and we would compare that to 1, and then it would be able to tell us these things right here. So I'm not going to spend too much time here. Don't let it overwhelm you. Okay, I'm going to skip all this stuff too. This isn't the basis of our learning today. Please take advantage of it if you would like. I'm going to skip down now past all this math. Good stuff though. And I'm going to skip to the wedge. We're going to do the wedge next week with wood splitting, like I mentioned. So jumping down here to the screw. What we want to think about with the screw is that it's just made up of 2 components. And so if we unwrapped, this visual shows us like an inclined plane as far as being a piece of paper wrapped around a pencil. This is great. Okay, so our 2 components are an inclined plane and then a wheel and axle for that rotation. And we'll talk about wheel and axle here in a week or so. So we really just want to look at this, understand the components, and if we have enough components with variables and we agree on how to identify screws, then we can set up nomenclature, and we do that in a lot of disciplines of science. So we're going to do that here as well. And excuse me, that's the main goal of today, is as a homeowner, understand how bolts, screws, and things are labeled, identified, so you can be a productive homeowner. All right. And then in blue, there's some of the properties we're thinking about. So yeah, pay attention in the real world. See if you can identify a screw like this over here on the right hand side, and see if you can see that in an adjustable table, like we have one on the router table. See if you can see that out in the real world somewhere in your workplace. At an industrial kitchen, you might see some things like that. Okay, so here's where hopefully you're paying attention. I know it's been 10 minutes, so I've lost most of you, but please direct your attention now to this here. And I forgot in one of my goals to put torque. So we're going to talk about a torque video at the end here. And with that, that's going to help us with this effort arm here where my cursor's at. And so that distance is going to allow torque, and then we have resistance built into the length of these, which I can kind of discuss a little bit further here. Down this line, this is the distance traveled. So that's going to have resistance when the bolt goes through the nut or through the threaded piece. And then so this is going to have resistance loss, and that's the distance we're worried about, that angle distance of that triangle. So when you're talking about geometry with Miss Haley and Mr. Vulich, this is some of the applied things you can think about. Okay, so back to screw identification. Thank you for letting me finish that thought. So thread information. Here is how we identify threads. So we go diameter first, and then we go threads per inch, and then we talk about whether it's a coarse or a fine thread. Okay, so diameter. The diameter is down here of the threaded part, not the head up top. So that's where it comes into even more play when you're trying to get the right tool, the right socket on the head to match the diameter. So that's when experience just comes into play. So diameter right there, we're going to see that as a fraction most of the time. We're just going to focus on standard measurement system for this identification. And then there's also metric too. So diameter, this is saying it has a 1/2 inch bolt. The next thing, 13 threads per inch. So threads per inch is I think shown, nope, not I thought there's a better visual. So threads per inch, just picture a distance from say the bottom to this line is 1 inch, and that's saying 13. So if we had 13, 1 inch here to scale, it actually be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So from the bottom of the bolt to where my cursor is, that would represent 1 inch scaled, and that's how many threads per inch, 13. And then the next thing is if it's fine thread or coarse thread we usually see for bigger things, outdoor things, fine thread, electronics, machine screws for your TVs, other things like that. So, all right, so the question at the bottom, and I already showed you the answer once or twice. How far will a screw with 13 threads per inch move linearly if turned one full rotation? So that hexagonal head at the top is just rotated once. How far will the screw move? And you could just use that as a fraction and say 1/13 of an inch, because 1 is representing the rotation and 13 was per inch. So that's how you do the math there. All right, again, a lot more on all this stuff. It's a lot of fun. I enjoy math. So let me know if you want to get into that. Great stuff. And then we can do some compound machines here too, once we're all said and done. And that's when we can get into bicycles and other things. So to wrap up this week's learning, I think it's important to talk about torque. So I'm ending with the two takeaways. Two takeaways this week are screw identification and torque. Those are the most important things for you guys as citizens and future homeowners. So in today's lesson, you should have this link. And so I want you to come to this video, and this is a crash course video put together by PBS, and it's been pretty beneficial. I think it's one of the more engaging and easier ones to follow around. And there's a smart young lady who's going to walk you through a little bit more as far as what rotational energy looks like with torque, because that's important in the shop when we use certain hand tools. So please finish out today with torque, crash course physics number 12. Have a good week. And please email me with the